So first, I will give the introduction that we are doing the course. The course title is Numerical Methods, Finite Difference Approach. The course instructor is Professor Amiya Kumar Nayak, and he is affiliated to IIT Roorkee. And I am the TA for this course. My name is Yudhvir Singh Yadav, and I am from IIT Madras. I'm a research scholar at IIT Madras. So, in the last tutorial, we have seen different finite schemes to in order to solve the parabolic partial differential equations, specifically parabolic PDs. So, in today's lecture, we will extend our previous lectures up to the second order partial differential equation. So, second order heat equation. We can say two-dimensional problems. So, in this tutorial, we will discuss how to solve a two-dimensional heat equation or parabolic partial differential equation. So for this purpose, we will consider a heat equation in two dimensions. Suppose del U by del T equals to del 2U by del x square plus del 2U by del y square. So here we have the spatial dimensions in both x and y, which is subject to some initial condition. Say u comma x comma 0 equals to some function of x and y. We can recall that like while studying for the one-dimensional heat equation, we have the initial condition is from ux comma 0 equals to function of x only. So here as we are talking about a two-dimensional heat equation, so we will take into account both the x and y dimensions. And the boundary conditions are give supposed as when x is 0, we have suppose G1, like we have a rod where x is 0 and x equals to 1 are both the ends. So at the other end where x is equals to 1, we have G2, and when y is 0, we name it as H1 x of x and t, and when y is 1, we will have H2, which is a function of x and t again. Here we have taken t greater than 0. So this is our basic system of second two-dimensional heat equation. Here we will take a uniform mesh of spacing h. We have taken a step size h in both the directions, one both x and y direction. So it will be we will take like x and y from 0 to 1, so it will be a square region. Where capital N denotes the number of nodes, whatever nodes we take. So H will be uniform for both the directions. And also we will take the step size in the time direction, that is t. So suppose k be the step size in the time direction. So say t equals to jk. As we increase j from like 1 to up to capital J. So we will take a increment in the time direction. Now the nodal points will be defined as XL, LH, Y will be MH, and Tn is NK. So here we have L equals from 0 to up to capital N. M is also from 0 up to capital N. And N we will take up to capital J. So we can even number these equations. Number 1, initial condition is number 2. These are our boundary conditions. And these are our nodal points. So basically, while we solve this using the finite difference scheme, so the solutions will be denoted by or appear as like the solution at u of function of x, y, and t at the nodal point xl, ym, and tn is denoted by u, l, comma, m, and n. So L and M are in the x direction and y direction respectively, and n is the number of steps in the time direction. So now we will try to construct a scheme for this heat equation 1. So like simply we will consider a scheme if we put if we use schematic scheme for the 2 dimension, then it will be like forward for time and central difference for both the space dimensions. So it will be UL, comma M, ULM, L minus 1. We are applying the second order central difference formula with respect to x direction. So it will be basically delta x square plus similarly with the y dimension, we will have 2 ULM, comma N divided by delta y square. Or we just can replace it the delta t by k, delta x by h square, and delta y square by also h square, as we have taken the uniform step size in both the directions x and y. Now, when you will simplify this further, where one can simply arrive at this scheme, which is obtained as UL at n plus 1 time step, UN lambda times delta x square, delta y square, theta ULM n plus 1, 1 minus theta. Oh, let us number it as 5. So this is a general form of some scheme. Here, thus above mentioned part is for the like schematic scheme for two-dimensional heat equation, and this next one, equation number 5, we have considered a general scheme. In this case, if you take theta equals to 0, so suppose we will make it as a case 1. Here, if it theta is 0, then what you will get is u l comma m to the power n plus 1, u l comma m n lambda delta x square delta y square, and as we have taken theta equals to 0, so this will be ul comma m comma n. So here lambda is again nothing but as we have taken earlier, it will be delta t by delta x square as a step size common, so it will be nothing but k by h square. And delta x and delta y represents the second order central difference schemes. That is delta x square of u is nothing but the second order central difference scheme with respect to the x direction. So I will write for the x, so it will be ul plus 1 comma m ul comma m to n plus ul minus 1 mn by delta x square. Similarly, you can extend it for y. So it will be ul m plus 1 minus ul m ul m minus 1 by delta y square. Or you can just simply h square and h square. So these are the notations that we have used to represent in a simplified manner. So from equation 6, if you extend it further, one can simply obtain a schematic scheme which will be u l comma m to power n lambda times u l plus 1 m n minus 2 u l m n plus ul minus 1 comma m n. Now similar way with respect to the y direction, it will be 2 lm n plus ulm minus 1 n. So this one is nothing but the schematic scheme, as you have already seen in the case of one-dimensional heat equation. So this one is with respect to the two-dimensional heat equation. Now one can take a note here that the order of accuracy is of k plus h square, as we have already seen in our previous tutorial, while we try to find the truncation error and the order of accuracy for the schematic scheme. So in this case, we already know that the order of for one-dimensional heat equation, the order of accuracy is given by k plus h square. So in similar fashion, for the stay, you can just simply try in the similar manner as we have done for one-dimensional heat equation. One can simply obtain this order of accuracy for this. So now we just talk about the stability of this schematic scheme for a two-dimensional heat equation. So for this, we will use von Neumann stability analysis. So here we will substitute the solution in form ul comma m to the power n as some xi to the power n e to the power iota beta 1 LH multiplied by e to the power iota beta 2 mH as with respect to the x and y direction. Here xi is the amplification factor as discussed earlier. So it should be like modulus of xi less than equals to 1 in order to be the scheme to be stable. So while in case of the one dimension heat equation, we were using only the this part, but in case of two-dimensional heat equation, we will use the solution in this form. Now, after you substitute this form in the solution, this equation number 6, you can directly arrive at this form of xi that as for one dimension case we have obtained some xi. So here you will obtain the xi in form of 1 minus 4 lambda times sine square of phi 1 plus sine square of phi 2, where phi 1 is beta 1 by beta 1 h by 2 and phi 2 is beta 2 h by 2. Now, these are just the notations we have used. You can simply, after simple calculations, one can arrive here simply. So for stability, we already know that for stability, we know that we must have xi such that modulus of xi is less than equals to 1. And hence, from above, as we have xi equals to 1 minus 4 lambda sine square xi 1 plus sine square of xi 2. So when we substitute this in our assumption, we will have minus 1, that xi is between minus 1 to plus 1. So it will be 1 minus 4 lambda sine square phi 1 plus sine square phi 2. It is between minus 1 to 1. Therefore, subtracting 1 from both the sides, we will have 0. Sorry. As we have all like as since we already know that sine square theta is always between 0 to 1. So we have sine square of phi 1 and sine square of phi 2 between 0 to 1 always. So the stability condition for the schematic scheme is obtained as that is for two-dimensional parabolic equation, that the lambda should be between 0 and 1 by 4. So this is the required condition for stability of schematic scheme with respect to two-dimensional heat equation. So up to now, we have discussed about the stability and the order of accuracy for the schematic scheme with respect to two-dimensional heat equation. Now we will see one more case. Like this is our equation 5 is our general form. So here we have taken theta equals to 0, then it will result into the schematic scheme. Now in equation 5, if we take theta equals to half, then we will see what happens. So we will take another case. Suppose theta equals to half, then equation number 5 gives ul comma m n plus 1, ul comma m n lambda by 2, delta x square, delta y square, ulm n plus 1 plus ulm n. So the equation number 5 gives us this form of different scheme. Or if you simplify this, or we rearrange in some certain form, then we will get 1 minus lambda by 2 times delta x square, delta y square, ulm n plus 1. That we have taken the n plus 1 time terms on the left hand side and all the other terms on the right hand side. So it will be ulm n, that is nth time step are on the right hand side and the n plus 1 time step terms are on the left hand side. Let us number this equation as equation number 8. Again, we can take a note here, as in the previous case for the one-dimensional heat equation. So in the order of accuracy for this will be k square plus h square. And it can be simply found by expanding these terms using the Taylor series expansion. One will arrive at this order of accuracy. Also, this equation number 8 is also scheme. This scheme is also known as the Kronecker-Nicolson scheme for two-dimensional heat equation. Now we will talk about the stability. As we have already seen in case of one-dimensional heat equation, that Crank-Nicolson scheme is unconditionally stable. So for the purpose of this case, we will again check for its stability. Now again using the von Neumann stability, that is the solution, we will just directly substitute the solution of form of this form into our Crank-Nicolson scheme equation number 8. So it will be xi to the power n multiplied by e to the power iota beta 1 mh beta 1 lh into e to the power iota beta 2 mh. Now substituting this, above form of solution in scheme 8 and simplifying further, one can arrive at that xi will be equals to 1 minus 2 lambda sine square psi 1 plus sine square psi 2. divided by 1 plus 2 lambda sine square psi 1 plus sine square psi 2. Again, we already know that sine square theta will always be between 0 to 1, and also we have lambda equals to greater than 0, as lambda is nothing but it is k by h square, and we have taken time greater than 0, so lambda will always be positive. Also, the condition for stability is that xi modulo should be always less than equals to 1, and above mentioned xi, we have 1 plus 2 times lambda, 2 lambda times sine square of phi 1 plus sine square of psi 2. So the denominator is always greater than, here one cannot, the denominator part will always be greater than the numerator. Therefore, xi is gonna always be less than 1. So again, we can simply say that the Craig-Nicholson scheme for two-dimensional heat equation is also unconditionally stable. So this is what we have talked about the different numerical schemes in order to solve the second order heat equation. But now we will discuss a different kind of numerical scheme, which is again used to solve the second order differential equation, second order heat equations. And we will see why this is much more efficient or differ, how it is different from the earlier schemes that we have discussed up till now. So our next topic is ADI scheme, or you can say alternating direction implicit scheme. Scheme, or you can say ADI method for solving two-dimensional heat equation. So first we will see why do we even need this ADI methods. So that these methods are two-step methods involving the solution of tridiagonal systems of equations along lines parallel to x and y axis at the first and second step respectively. So like this is a short description of this method, ADI method. Uh, the main difference is you can, like while solving the two-dimensional heat equation using the Crank-Nicolson scheme or the skimmed scheme, we will obtain a pentadiagonal matrix which again will be difficult to solve as we have already know how to find the solutions for a tridiagonal matrix. It will be a system of equations which will be easier to solve, and in order to find the eigenvalues for a tridiagonal matrix, it will be much more easier than that of the pentadiagonal matrix. So this will be one of the benefit of using the ADI methods in order to solve two-dimensional heat equation uh, instead of using the Crank-Nicolson scheme or the skimmed scheme. So the ADI methods will result into tridiagonal matrices like whose form are this. So the lines represents the non-zero entries and the zero other entries are all zero, whereas the Crank-Nicolson scheme and the skimmed scheme gives us a pentadiagonal matrix. Like five diagonals will be having the non-zero entries and the other entries are zero. So that's why we will use the ADI method in order to solve a two-dimensional heat equation problem. So first we will see the construction of this ADI method. This is also known as Peaceman-Rackford ADI method. So we will see the construction of this method, how we develop a finite difference scheme named ADI method. So in this, the first step the first step is advancing form, that in which we will go from Tn to Tn plus half, and the implicit differences are used, like we will use implicit difference scheme for Uxx and explicit difference scheme for Uyy term. So for this purpose, first we will consider a two-dimensional heat equation, that is del U by del T equals to del 2U by del x square plus del 2U by del y square. So according to the first step, we will have that using the forward scheme, again simply the forward scheme for the time step, that is n plus half minus ul comma m by n. It is k by 2 equals to delta x square by h square ulm comma l comma m n plus half plus 1 by h square del y square ulm comma n. So here this term we have taken the time step as n plus half. As I have mentioned here that we will use implicit difference scheme for the uxx, that is the time step level at which we are finding the value. And for uyy, we are using the explicit difference scheme which represents the time step at which we already know the value at that point. So in this ADI scheme, we will be proceeding in two different steps. First, n to n plus half, then n plus half to n plus 1. Here, k and h are the step sizes in the time direction and x and y respectively. Now we will see the second step. In second step, we will march from Tn plus half to Tn plus 1, and we will use explicit difference scheme for both uxx and uyy. So this will result into ul comma m n plus 1 minus ul comma m n plus half k by 2 1 by h square delta x square ulm n plus half plus 1 by h square del y square ul comma m n plus 1. So I have made a mistake here. We are using the explicit difference. In this case, we are doing it in the reverse manner, that we will use explicit difference for uxx and implicit difference for uyy. So let us denote with star and this with double star. So these are the two steps that are involved while solving any two-dimensional heat equation using the ADI method. So that first we will march from the time step n to the n plus half, and then we march from n plus half to n plus 1. So there will be two steps involved while going from n to n plus 1. Now I will simplify this. So we set lambda equals to k by h square. Therefore, we will have 1 minus lambda by 2 delta x square u l comma m n plus half. So this is just a simpler form of writing the above equation, that is star and double star. And it is numbered 1. And the second step is 1 minus lambda by 2 delta y square ul comma m n plus 1 1 plus lambda by 2 delta x square ul comma m n plus 1 half. So one can note that these two steps are involved. Here n plus half doesn't have any exact meaning in solving those equations, so it is just an artificial time level that we have introduced. So we can also say that n plus half is an artificial time level that we have introduced for our convenience in order to convert the solution or the system of equations in a tridiagonal form. And it is not a part of the mesh grid. So this is just an artificial time step. Now we can also reduce this equation 1 and 2 into a single equation also by just simply adding both of these, which will result into ul plus m, ul comma m, n plus half will be 1 by 2, 1 by lambda by 2, delta y square, ul comma m, n plus 1 by 2, 1 minus lambda by 2, delta y square, ul comma m, n plus 1. So this is another equation or a simplified way to write the ADI scheme. Simply, you can just introduce the boundary conditions also and simplify this scheme further. Like one more way to write this scheme is 1 minus lambda by 2 delta x square, 1 minus lambda by 2 delta y square, u l comma m n plus 1, and 1 plus lambda by 2 delta x square, 1 plus lambda by 2 delta y square, ul comma m n. So let us number it equation number 4. So in this we have just the time step levels n plus 1 and n. So this is the most simplified way to write the ADI method in terms of only n plus 1 and n. We have removed the artificial time level that n plus half. So one can also see the stability of the scheme. So let the solution of the form again that ul comma m to n is I to the power n e to the power iota beta 1 LH plus e to the power iota beta 2 MH. So when you substitute this form of solution in the equation number 4 and simplify, then we will have the amplification factor xi in terms of 1 minus 2 lambda sine square psi 1, 1 minus 2 lambda sine square psi 2 divided by 1 plus 2 lambda sine square psi 1 plus 1 plus 2 lambda sine square psi 2. Now again, since we know that sine square of theta is always between 0 to 1 and the denominator have a plus sign whereas the numerator has a negative sign. So the denominator is always greater than the numerator in this case, which will imply the above the ADI scheme or ADI method is unconditionally stable. So this scheme is a better option to in order to solve a two-dimensional heat equation in a more efficient and easier way, as it is also an unconditionally stable scheme. Now we will see some problems on this method. So let us consider a question. Find the solution of the two-dimensional heat equation. So this is our heat equation in 2D form, and the initial conditions are given as so here we have sine pi x and multiplied by sine pi y, and x and y are between 0 and 1, and the given boundary conditions are u equals to 0 on the boundaries. T is always greater than equals to 0. So you can think about solving how to solve this problem, or we will see that we have to solve this 2D heat equation with the given initial and boundary conditions using an explicit scheme. And the given scheme is u element plus 1, 1 minus 4 lambda u lm n plus lambda times ul minus 1 mn ul plus 1 mn plus ul m minus 1 n plus ul m plus 1 n. So this is an explicit scheme that we have to use in order to solve the above problem, and the step sizes are given as h equals to 1 by 3 and the lambda is given as 1 by 8. So the question is investigate up to 2 time levels and compare the obtained result or compare the obtained numerical value with the exact solution. And the exact solution is given as u as a function of x, y, and t, e to the power minus pi square t sine pi x sine pi y. So this is the complete question that we have to solve here. So in this, we have to use this explicit method, a given explicit method with the given step size and the value of lambda, and we have to solve up to 2 time levels and compare the numerical solution with the given exact solution, that how close we have obtained the solution. It will also uh, represents the accuracy of the method also, or accuracy of the given explicit scheme. So now we will see the solution for this. So consider, as we have lambda is given 1 by 8 and h is given 1 by 3. So one can simply find the value of k here. So as we have lambda is nothing but k by h square, so it implies k is 1 by 8 times 1 by 9. So k is nothing but it is 1 by 72. So this is the step size in the time direction, that is 1 by 72. And the given scheme is u l comma m n plus 1. So here we have lambda is this. So when we substitute these values, that lambda equals to 1 by 8 and value of the step size is h and k, this explicit scheme reduces to half ulm n plus 1 by 8 ul minus 1 and ul plus 1 m and ul m minus 1 and ul m plus 1 n. So here we see, so let us number this as equation as scheme as equation number 1. Further, we also have the initial and boundary conditions. So initial and boundary conditions. So we will first convert them into the finite difference schemes. So initial condition is x comma y comma 0, which can be written as u l comma m and 0 at the t's place. Since it is a time is taken 0, so n will be 0, and it is given by sine pi l by 3 sine pi m by 3. Since x is nothing but LH, as we have seen, x is LH and y is MH, and h is 1 by 3. Therefore, we will get the initial condition as sine pi L by 3 and sine multi multiplied by sine pi m by 3. And the boundary conditions are u L comma 0 with power n, that is at for each time step, u 0 comma m, that when x and y are 0, equals to u 3 comma m equals to u L comma 3 is equal to 0, as it has been given in the question. That boundary condition is n u equals to 0 for all on the boundary. Uh, how we have taken it is 3 to 0. So this is 0 and the ending point is 1. Since h is 1 by 3, so these are the points, that is 1 by 3, 2 by 3, and 1. So the nodal points are 0, 1, 2, and 3. So at 0 and 3, we have the values of u equals to 0. So these are the simplified initial conditions and the boundary conditions. Also, we can have for the initial conditions that u11 comma 0 as sine pi by 3 multiplied by sine pi by 3 goes to 3 by 4, and u2 comma 1 0 is also 3 by 4. You can just simply solve this part and obtain these values. So we will first write all the values that we can simply find from the given data. And at n equals to 0, we have u120 equals to 3 by 4 and u2 comma 20 equals to 3 by 4. So these are the values that we already know on our grid. So next we will see what we have to find. So at 0 time step, we already find all the already obtained all the values. So now we have to proceed up to 2 time steps. So first, take n equals to 1 or n equals to 0. So the scheme 1 will result into ul comma n 1 1 by 2 ul comma m 0 1 by 8 ul minus 1 0 ul plus 1 m 0 u l m minus 1 0 u l m plus 1 0. So this is the scheme. Therefore, now we will just simply substitute all the values that we already know. So when L and M both 1, then we will have U1 comma 1 1, U1 comma 1 0, U0 comma M 1 0, U2 comma 1 0, U1 comma 0 0, U1 comma 2 0. So we will just place the values of the terms that we already know from the initial and boundary conditions. So it will be 1 by 2 times 3 by 4 plus 1 by 8 times 0 plus 3 by 4 plus 0 plus 3 by 4. So it will be 9 by 16. So after just simply substituting all the known values in this expression, we will obtain the value at the first time level at the point 1 comma 1. Here we have taken L and M as 1. The next step is we take L equals to 2 and M equals to 1. in this above equation, then we will have u2 comma 1 1 1 by 2 2 comma 1 0 1 by 8 u1 comma 1 0 u3 comma 1 0 u2 comma 0 0 u2 comma 2 0. So again, we will substitute the known values in this expression. Therefore, we will get 1 by 2 times 3 by 4 plus 1 by 8 times 3 by 4 plus 0 plus 0 plus 3 by 4. So we will obtain again 9 by 16. So the another value is 9 by 16. Now we will take L equals to 1 and M equals to 2. So we will have u1 comma 2 1 equals to 1 by 2 times u1 comma 2 0 1 by 8 u 0 comma 2 equals to 0 u2 comma 2 0 u1 comma 1 0 and u1 comma 3 0. Now again substituting the known values, we will get 1 by 2 times 3 by 4 plus 1 by 8 times 0 plus 3 by 4 0 plus 3 by 4 0, which is nothing but 9 by 16. And similarly, when we take L equals to 2 and M equals to 2, we will have u2 comma 2 1 1 by 2 u2 comma 2 0 1 by 8 u1 comma 2 0 plus u3 comma 2 0 plus u2 comma 1 0 plus u2 comma 2 0, and after substituting all the values we will get 9 by 16. You can simply verify these calculations. Now for the second time step we will take n equals to 1. Here as we have to find up to the 2 time steps. Now for the second time step, the equation number 5 scheme is reduces to ul comma m n to the power 2 1 by 2 ul comma m 1 plus 1 by 8 times ul minus 1m plus ul plus 1m plus ulm minus 1 plus ulm plus 1. Now first we will take L equals to 1 and M equals to 1 in this equation. So it will be U1 comma 1 2 1 by 2 U1 comma 1 1 1 by 8 U0 comma 1 1 U2 comma 1 1 U1 comma 0 1 plus U1 comma 2 and 1. So here we are finding at the second time step, and we already know the values at the time step n equals to 0. That is the first time step, and we will use the previously obtained values in order to obtain the values of the next time step, that is n equals to 1. So we will substitute these known values. So once you substitute, then you will get 9 by 32 plus 1 by 8 times 0 plus 9 by 16, 0 plus 9 by 16. So the final value will be 27 by 64. Now we will take L equals to 2, M equals to 1. So it will be 2 comma 1, 2, 1 by 2, 2 comma 1, 1, 1 by 8 times 1 1 U3 1 1 U2 0 1 and U2 2 1. Now substituting these values, we will get 9 by 32 plus 1 by 8 times 9 by 16 plus 0 plus 0 plus 9 by 16, which will be again equals to 27 by 64. And in similar way, we will take L equals to 1 and M equals to 2. Then the scheme will be U1 comma 2 2 1 by 2 times U of 1 comma 2 1 plus 1 by 8 U0 comma 2 1 U2 comma 2 1 U1 comma 1 plus U1 comma 3 at time step 1. So substituting these values, we will get 9 by 32 plus 1 by 8, 9 by 16 plus 0 plus 9 by 16 plus 0. So it will be 27 by 64. In similar way, we will take L equals to 2 and M equals to 2. Then the scheme will be U2 comma 2 at the second time step, 1 by 2, 2 comma 2 at the one time step, 1 by 8 times 1 comma 2 1 plus 3 comma 2 plus U2 comma 1 plus U2 comma 3 1. So these are the already known values. So it will come out to be 27 by 64. So these are just a simple calculations and you can verify with these by yourself. So these are the values that we have obtained up to the second time step using the given explicit scheme. You can verify this calculation by yourself also. It will be good for the practice. And simply you can substitute the values in the given exact solution and compare it with your numerical solution. Now we will discuss one more problem. So consider a heat equation, a 2D heat equation. It is del U by del T plus del 2U by del X square plus del 2U by del Y square. So this is our standard as two-dimensional heat equation. And the given initial conditions are Ux comma Y comma 0 equals to sine pi x multiplied by sine pi y. So this is nearly the same problem as the previous one. And boundary conditions are U equals to 0 on boundaries. So in this case, we will use the Peaceman-Rackford ADI method, and we will see how it is simpler to solve in this way. So using the Peaceman-Rackford ADI method, investigate up to one time level. So this is a given problem. Here we again solve the same 2D heat equation, but this time we will use the ADI method in order to solve this problem. Also, given that h is 1 by 4 and lambda is 1 by 8. So these are the given step size and our constant lambda, where again, as you know, that lambda is nothing but k by h square. So first we can simply find k. K will be 1 by 16. And this will be our k. Now we will see the solution for this problem. Here we will use the ADI method. So first we will see the nodal points. So the nodal points are given by that XL in the x direction. It is L by 4, which is nothing but LH. So H is given as 1 by 4, it will be L by H. And YM is M by 4. So L is nothing but 0 to 4 and M is nothing but 0 to 4, since X and Y are between 0 to 1. So there we will be having a heat rod from 0 to 1. So 1 by 4, 1 by 2, 3 by 4. Nodal points are 0, 1, 2, 3, and 4. So the respective initial and boundary conditions can be written as UL comma M to 0 sine pi L by 4 sine pi M by 4, and the boundary conditions are UN plus half is equals to, at when L equals to 4, N plus half will be 0, and at N plus 1 are 0, where M and L are 0 to 4. And the step size is 1 by 4, where the total number of points are 5. Up to 0 to the 0, 1, 2, 3, and 4. Now, what is the Peaceman-Rockford scheme? So the Peaceman-Rockford scheme is, since it is a two-step method, so the first step is 1 minus lambda by 2 delta x square ul comma m n plus half, that we will first find the values at the time step n plus half and then use that one in order to find the solution at n plus 1. So on RHS it is 1 plus lambda by 2 del y square ulm n. This is our first step. And the second step is 1 minus lambda by 2 del y square ulm n plus 1. That is a required time step that at which we have which are at which we are required to find the solution, that is n plus 1 at time level. It is 1 by lambda by 2 delta x square ul comma m n plus half. So these are the two steps that we will use in order to find the solution using the ADI method. That is also lambda is given 1 by 8. Therefore, we will have, therefore the equation 1 and 2 reduces to 1 minus 1 by 16 delta x square ul comma m n plus half 1 plus 1 by 16 ul comma m n, let us number it 3, and equation 2 will reduce to 1 plus 1 by 16 ul comma m n plus half. So let us number it equation number 4. So these are the simpler equations. Now we will start to find the solutions. So first we will take n equals to 0. Taking n equals to 0, then we get the solution of ul comma half. So we will take n equals to 0. So we will have from equation number 33, equation 3, we will have delta x square ul comma m half 1 plus 16 delta y square ul comma m 0. So if we expand these terms, that we have represented the central second order difference scheme by delta x square and delta y square. So on expanding these, we will get ul comma m half minus 1 by 16. Expanding this, we will get ul co l plus 1 m half minus 2 ul comma m half plus ul minus 1 m half equals to ul comma m 0 at 0 time step plus 1 by 16 ul m plus 1 0 ul m 0 plus ul m minus 1 at 0 time level. So simplifying it further, taking the half or simplifying it further, taking the common terms together, we will get minus 1 by 16 u l m l minus 1 m half plus 9 by 8 u l m half minus 1 by 16 u l plus 1 m half equals to 1 by 16 u l m minus 1 0 plus 7 by 8 u l m 0 plus 1 by 16 u l m plus 1 0. So this is the most simplified version of this equation. So we will try to solve this one in order to find the solutions at the half time step. So first, on first mesh line, it is m equals to 1. We get that is for l equals to 1. We have 1 minus 1 by 16 u 1 half plus 9 by 8 u 1 comma 1 half minus 1 by 16 u 2 comma 1 half equals to 1 by 16 u 1 comma 0 0 plus 7 by 8 u 1 comma 1 0 plus 1 by 16 u1 comma 2 0. Here what we have done, we have taken the first mesh line, fixed m equals to 1, and then we will keep on changing the values of L or the nodal points in the x direction. Similarly, for the L equals to 2, one will have 1 by minus 16 u1 comma 1 half plus 9 by 8 u2 comma 1 half minus 1 by 16 u3 comma 1 half, and on the RHS you will have 1 by 16 u2 comma 0 0 plus 7 by 8 u2 comma 1 0 plus 1 by 16 u2 comma 0 0. It will be u2 comma 2 0. So since we have the step size is equals to h1 by 4, therefore we will have total number of nodal points we have is 5. So we know the values at L equals to 0 and at L equals to 4. So we need one more uh, unknown, we have one more unknown nodal point, that is L equals to 3. So for this, we will have the equation 1 by 16 u2 comma 1 half plus 9 by 8 u3 comma 1 half minus 1 by 16 u4 comma 1 half, and on the RHS we will have 1 by 16 u3 comma 0 0 plus 7 by 8 u3 comma 1 0 plus 1 by 16 u3 comma 2 0. So this is a set of equations which contains the unknown points that we are required to be found, or some of we already know at the times level 0 from the initial condition. So we will simply substitute values of the known terms that are the 0 time level, and the using the boundary conditions and the initial condition, one will obtain the following system of matrices, which can be written as a system of matrix as 9 by 8 minus 1 by 16 0 minus 1 by 16 9 by 8 minus 1 by 16 0 minus 1 by 16 9 by 8 multiplied by u1 comma 1 half u2 comma 1 half and u3 comma 1 half equals to, so the right hand side values, as we already know, using the initial conditions and the boundary condition. So this comes out to be 7 times root 2 plus 1 by 2 root 2, 14 plus root 2 divided by 16 root 2, 7 times root 2 plus 1 divided by 16 root 2. So these are the unknowns that are required to be found. So now, after substituting all the known values, we will arrive at the simple 3 cross 3 system of equations. So this is also, you can note that this is a tridiagonal system. You can either find the, also you can also find the eigenvalues for this. But in our case, we only need to find the values of the unknowns in the given vector, which I have mentioned as unknowns. So you just have to simply solve this system to find the values. So the values, once you solve, I will just write the final answer, and you can compare with with yours. So the final answers are obtained as u1 1.5 and u3 1/2 are obtained as 12.7 Sorry, it is 127 plus 16 root 2 divided by 322, which in decimal form is obtained as 0.46468. And U21 half is obtained as 0.65716. So you can compare with the solutions that you will just you have to replicate the procedure that I have done, and you must arrive at the solution of this form. So now the second step is what as we have considered up to m equals to 1, as we have earlier fixed m equals to 1. Now we consider the second mesh line, that is m equals to 2. So we will get again we have to do the same procedure that we have just done, that we will take L equals to 1, 2, and 3 respectively, and therefore we will get a system of uh, three equations that can be written in a matrix form as below. It is 9 by 8, minus 1 by 16, 0, minus 1 by 16, 9 by 8, minus 1 by 16, 0, minus 1 by 16, 9 by 8, and the vector is unknown vector is 1 by 2 half, 2 comma 2 half, 3 comma 2 half. On the RHS we have the known values 7 times root 2 plus 1 by 16, 14 root 2 by 16, and 7 root 2 plus 1 by 16. So again, this vector is the unknown vector of unknowns that are required to be found. So again, here it is. This is a tridiagonal system. This is the benefit that I have noted initially while discussing the ADI method. That in this ADI method, one will always end with a tridiagonal matrix, which is easier to solve with as compared to the pentadiagonal matrix. So once you solve this system, you must obtain the solutions in the form as this. You can just simply cross-check these answers by yourself, solving the given problem by yourself. So the solution is 127 times root 2 plus 32 by 322, which will be equals to nothing but 0.65716, and u2 comma 2 will be 0.92926. So you can cross-check your answers for this particular mesh line. Again, as we have M and L 0, 1, 2, 3, and 4. So 0 and 4 we already know. As you can see, 0 and 4 are the boundary points. So we already know the values at these points. 1 and 2 we have done that, we have fixed m equals to 1 and m equals to 2. Now we will fix m equals to 3. Now fix m equals to 3, or we will consider the mesh line where m is equals to 3, and taking L equals to 1, 2, and 3 respectively, we get again a system of three equations and in a matrix form. I will just directly write the matrix form notation. You can solve for each time step and each mesh line and check with the corresponding answers. So it will be 9 by 8 minus 1 by 16, 0, minus 1 by 16, 9 by 8, minus 1 by 16, 0, minus 1 by 16, 9 by 8. And the unknown vector is u1, comma 3 half, u2, comma 3 half, and u3, comma 3 half, that we are finding at the half time step. And on the RHS we have 14 plus root 2 divided by 32, 7 root 2 plus 1 by 16, and 14 plus root 2 divided by 32. So, and the final answers that you can also cross-check with yours are as obtained as u1, comma 3 half, u3, comma 3 half will be same, which is nothing but 127 plus root 2 divided by 322, and it is nothing but 0.46468, which is similar to the first mesh line, that is m equals to 1, and u3, u2, comma 3 at half times level is 0.65716. So these are the solutions up to half time level that we have obtained, but our target was to find at the time level 1. So now we will use the second step of the ADI method, at which we have the n plus 1 time level, and we try to find n plus 1 using the n plus half time levels. So we have already obtained the n plus half time level solutions. So we use these ones in order to find the n plus 1 time levels. So we have a solution of ul comma m1, that is nothing but ul comma m n plus 1 at n equals to 0. So the equation number 4, so this equation number 4, now we will use this one as our second step. So we will put n equals to 0 in equation number 4, and it will reduce to minus 1 by 16 ulm minus 1 1 plus n by 8 ulm 1 minus 1 by 16 ul m plus 1 1 equals to 1 by 16 ulm l minus 1 m half plus 7 by 8 ulm half plus 1 by 16 ul plus 1 m half. So as we have done at the first step of the ADI method, we just have to repeat the similar steps for the second step. The difference between both are these. Earlier we know the solutions at the time 0th time level, and we found the solution at the half time level. But in this step, we need to find the solution at the 1th time level, that is n plus 1. And in the first step, we find out the half time level solutions. So we will use those in order to find the solutions in this step. So here you will have to do the similar procedure. You have to follow the similar procedure, that fix m equals to 1, then 2, then 3. And for each m, you have to take L 1, 2, 3, 1, 2, 3, and L 1, 2, 3. So there will be like 3 different cases for each m value. So like if I write for the first one, you will get a system of the form 9 by 8 minus 1 by 16, 0, minus 1 by 16, 9 by 8 minus 1 by 16, 0, minus 1 by 16, 9 by 8, u1 comma 1 1, u1 comma 2 1, u1 comma 3 1. And on the RHS you will get 0.44767, 0.6331, and 0.4476. So this is the case when we have fixed L equals to 1 and changed the values of M. So you can do you can do in whichever way you feel more convenient. The solution is gonna be same. So then the solution will be obtained as u1 comma 1 is equals to 0.43186, u1 comma 2 is 0.61074, and u1 comma 3 is 0.43186. Now for the other case, that is when L equals to 2 and M are changed from 1 to 3, the solutions are, I will just write the final solutions. Calculation part you can do, or it won't take much time. You just have simply need to solve a tridiagonal system of matrices. So it will be u2 1 comma 1, u2 comma 3, and u2 comma 2. So the values are 0.61074, 0.61074, and for this term, the solution 0.86371. Now the third case, when L is 3, and you have to change for 1, 2, and 3, the solutions are u3 comma 1 1, which is 0.43186, u3 comma 2 is again 0.43186, and u3 comma 2 at first time step is obtained as 0.61074. So in this way you can find the solutions of a two-dimensional heat equation using the ADI method or the Piecemeal-Rackford ADI method. So you can cross-check with the solutions by calculating these by yourself, and also if you use the Crank-Nicholson scheme or the Schmidt scheme, you will be troubled to find out the solutions more accurately, as you have to solve a large system of unknowns or the pentadiagonal matrices. So it will take much more longer time to solve for the particular problem or a two-dimensional heat problem. So it will be much more advised to solve the problems using the ADI method, as it will also help in order to find the stability of such scheme as it reduces to a two tridiagonal systems. Next, we take one more question. The question says, consider a heat equation that is ut uxx plus uyy, which is valid in domain. The given domain is where x and y are from 0 to 1 and time is greater than equals to 0. The initial and boundary conditions are given as sine 2 pi x, sine 2 pi y, and the boundary conditions are u as a function of x, y, and t equals to 0 for all t greater than 0 on boundary. Now you have to solve the above heat equation using the ADI method with the step size h equals to 1 by 3 and lambda equals to 1 up to one time level. So up to one time level, you have to solve this given problem using the ADI method. So I will just give a simple outlook for this problem that then you can try it by on own, and either you can ask in this if you're unable to solve this in the next session. So what is given here is h is given 1 by 3, lambda is 1, which will imply k equals to lambda h square, that is nothing but 1 by 9. So the time step, the step size in the time direction is nothing but 1 by 9. And as it is given that the step size, the domain is 0 to 1, so it will be 1 by 3, 2 by 3, and 1, and the nodal points are 0, 1, 2, 3. Also, it says that the boundary condition is that on the boundary it is 0 at all boundary points. So, like more generally, you will have this kind of grid. So at these points, so these are the boundary points. So at boundary it is 0. So u is 0 here, 0 here, 0 here. All these points that are on boundary, u is 0. So the only points that need to be found are these ones. So this one is nothing but u1 comma 1, u1 comma 2, u2 comma 2, and u2 comma 1. And time step at whatever you have to find that it is given as time step at we have to find at the one time level. So these are the unknown points that we have to find using the ADI method, and using the given data in this question we have up to these terms solution for these. So you can just simply proceed with these solutions, that is using the initial conditions we will be having, or I will just write it that initial condition we have sine 2 pi LH, sine 2 pi MH, which is nothing but sine 2 pi L by 3 and sine 2 pi M by 3, or for the required points that we have the from initial conditions we will have sine 2 pi by 3 and sine 2 pi by 3. It is nothing but 3 by 4, that root 3 by 2 and root 3 by 2. Similarly, U210, U120, and U220 all are 3 by 4. You can find it out. And from the boundary conditions, what you have is at U L comma 0, that when y is 0, and at U L comma 3, at the m is 3, you will be having 0, and 0 comma m, and 3 comma m for all time step it is 0, n is greater than equals to 0. So these are the given values. Those are given, or this is a data that we can obtain from the given inputs in the question. So you can just simply use these values in order to find all the unknowns that I have shown here in the grid points, that you have to find the values of u1 comma 1 up at one time step. So what you will do is, using these values, you first use the step 1, that you have to find at the time step at t equals to half, using the values known at t equals to 0. Then using those values of at t equals to half, you will proceed to find the values at t equals to 1. So in this way, you can simply find the solutions for the first time step. As I asked in this question, you have to find up to only one time level. You can even proceed further for different time levels. So this is all about the ADI method and how to solve the two-dimensional heat equations more efficiently. Thank you for joining. We will discuss the upcoming questions in the next session. And if you have any doubt, you can ask in the next session to me. Thank you for joining. Now I will end the meeting.